Okay, let's start the lecture today. So let's first wrap up the remaining things in multi-agent reinforcement learning, and then today we'll talk about partially observable reinforcement learning. So in the last lecture, we talked about multi-agent reinforcement learning, and especially we talked about two unique challenges. The first one is curse of multi-agency. That is, we typically, if we just design like a prior algorithm, and the sample complexity or computation is going to grow exponentially with the number of agency, which is definitely a problem if we have like reasonable number of agents. For example, we have 10 agents or 20 agents, and then exponentially in 10 or 20 is like very difficult to accept. And the second one is we want to design a decentralized algorithm. When we have a lot of agents, it's better to have a decentralized algorithm so everyone just play on their own instead of having a centralized player and coordinating everybody, and that's like pretty difficult. So we kind of asked the question whether we can design some decentralized algorithm that breaks the curse of multi-agency. So we start from the normal form game. Where we essentially say the answer to do this is just a no-regret learning algorithm. For example, in the last lecture, we introduced the algorithm called EXP3, essentially just doing exponential weights, which are able to achieve no regret even given the adversarial opponents. And this guaranteed to converge to a CCE in the general sum setting and the Nash in the two-player setting. Two-player zero-sum, and this is a multiple player. So in the end, we also talk about, this is only about normal form game, which has no states or transition. So in this class, we care a lot about the model or the problem that have temporal structure in it, which we look at the Markov games. And in Markov game, unfortunately, there's no regret learning. Like there isn't any like polynomial efficient no regret learning algorithm. So we kind of say anything suffer like sublinear regret would pay something exponential in A or horizon, which is definitely unacceptable. But the good thing is we still have this is like only a sufficient condition to find a Nash equilibrium or CCE. We still can leverage the idea of no-regret learning to design an algorithm for finding Nash or CCE. Okay. So this is still doable, although no-regret learning is no longer possible. No-regret learning in terms of entire Markov game is no longer possible, but finding Nash or CCE of the Markov game is still doable. So the algorithm we studied in the last lecture is called the V-learning algorithm. It's very similar to Q-learning algorithm with only like two major changes. The first one is, this is similar to Q-learning. The first change is essentially we estimate V-value instead of Q-value. We still do incremental updates, like 1 minus alpha fraction of the previous V-value plus alpha fraction of the new updates. But the only difference is now we estimate V instead of Q. So what do we lose by the good thing about estimating V is like a V is like Q in the multi-agent setting in general should be like, it depends on the joint action, which is exponentially large. Well, V is only depends on states, so still have reasonable size. But on the other hand, the bad thing about only having the V is we no longer have the policy. So that's why we need the second step. We essentially have a state-wise no-regret learning algorithm. That is, we no longer pursue a no-regret learning for the entire game, but we pursue no-regret learning for each state. we use an EXP algorithm for each state to compute the policy. So those two combined together function as a Q. Okay, so Q has both value and a policy. While here we estimate V and then use no-regret learning as a good policy. I think good thing is now we can like embed this no-regret idea into the algorithm so that the algorithm has some ability against like a certain adversarial. It's not like adversarial player of a Markov game, but like certain state-wise adversarial thing, so that eventually we're able to find Nash and CCE. Okay, so basically we stopped here in the last lecture. So we're formally talking about the guarantees. So essentially, algorithm is very simple. We already said V-learning is a single agent algorithm. We kind of similar to Q-learning, so there's a single agent. In a multi-agent setting, the algorithm is very simple. It's just everybody run V-learning simultaneously. So the algorithm is all agents run V-learning simultaneous independently. So as if the other player not existent, other players just environment. We say typically if we just run standard single agent reinforcement learning algorithm, that won't work because that usually assumes the environment is stationary. But the V-learning has the power of no-regret learning, like has certain way of dealing with adversarial thing. So this algorithm actually will work in a multi-agent scenario. So the theorem is follows. So we have two theorems here. It's kind of like similar to the no-regret learning algorithm in the normal form game. So first theorem is in the two-player zero-sum game. Markov games, V-learnings. We'll find epsilon Nash. In this O tilde of h to the fifth s max A1, A2 over epsilon square episodes. If you remember, in the last lecture, we say the sample complexity guarantee for the standard like Nash value iteration, and the sample complexity would be some poly H times S and times A1 times A2, the product of the action. Now here we kind of we improve it to the max A1, A2, so this already achieved essentially achieved the lower bounds in this A1, A2. Okay, so basically here the A1, A2 dependency. We say in the last lecture, we also say that for two-player zero-sum game, there's a lower bound, information theoretical lower bound. You can prove it's like max A1, A2. So this essentially already achieved the lower bound, except for some like polynomial dependence on H. Here, the V-learning is not very sharp, and there are some better ways, like insert some better no-regret algorithm, and which are able to improve the H dependence. So similarly, we will also have a guarantee for CCE in the multiplayer general sum scenario. So in general sum, Markov games, V-learning finds epsilon approximate CCE in, again, O tilde, h to the fifth, s, and max I, AI. over epsilon squared. So interestingly, this dependence actually doesn't like explicitly depends on M if every player's actions, the number of actions for every player is the same. Okay, this will just be A. Okay, so the conclusion is basically by just tweaking Q-learning in this way, we're actually able to design a decentralized algorithm that breaks the curse of multi-agency. So essentially solve the two challenges we talk about. I just want to comment that in the last lecture, we also mentioned there are three different equilibrium. One is the Nash, the other one is CCE. But in correlated equilibrium, there are like one is like a vanilla correlated equilibrium, and this is like coarse correlated equilibrium. So the only difference, like when you betray other player, whether you can still observe the random coin that is given to you. So it turns out if we want to solve for God, so for CE, sorry. Theorem 3. Or we just say for epsilon CE, if we don't really care about the CCE, we want to find a correlated equilibrium, we can also do that. And the trick is just slightly different. That will replace no regret algorithm within this V-learning, we run state-wise no-regret algorithm. Like for each state, we maintain a no-regret algorithm. We replace this by so-called no-swap regret algorithm. Okay. It's a little bit more involved. I don't want to go into details of what is no-swap and no-swap regret. That's like a little bit more involved. But basically, you can think it's kind of very modular as long as you change this algorithm component by some like algorithm with a slightly stronger guarantee, and you're able to find CE instead of CC. Okay, and this roughly wrap up the everything we want to talk about for multi-agent reinforcement learning. If you have any questions, feel free to ask. Yeah, otherwise, we will proceed to the final topic of this course. That's partial observability. So far, we're focused on the fully observable problem. Essentially, for so many lectures, we're basically just focusing on two mathematical models. The first one is a Markov decision process. The other one is Markov games. Okay. But for both models, we assume the learning agents or the player are directly able to just observe the underlying states, which is like states will go through some Markov transition. And but in practice, there are a lot of scenarios which is partially observable. We can think of some examples like when we play a poker card game. The state can be basically described by the cards in my hands, the cards on the table, and the cards in my opponent's hands. However, when we play the game, we're only able to see the cards in my hand and the cards on the table, but we're not able to see the cards on the opponent's hand. So in that case, we don't fully observe the underlying states that go into Markov transition. We only partially observe the information. So in that kind of scenario, this is like called partially observable. Similar kind of application, like for example, when we play some video games, like when we play StarCraft, there are some like war fog or fog of war. Basically, we don't like unless we have some like scouting units go to the other player's base, we don't really see like what other player is doing. And finally, like if you want to do some robotics, a lot of times it involves like sensing and how the robot's gonna know the environments. And typically, one very like popular way of doing sensing is like you have the first-person camera of the robots. And in that case, robots only observe what's in front of the robots. And for whatever like on the side or behind the robots, they have no idea. So in that kind of scenario, the entire state is described by everything in the environment, but the robots only be able to see something in front of it. It isn't really able to perceive what's behind it or something change behind it. So this is like partially observable environment. So basically, many applications are partially observable. So when we partially observable, we're saying the latent states. So for those games or those applications, whatever going to a Markov transition is the states, but because it's we only observe part of it, so it's kind of like latent states. Okay. So as a foundation of reinforcement learning, the first question is always, now we know this need of like practical applications, then how are we going to model those applications? Like we know this kind of like definitely fall beyond our existing model like MDP and Markov game. We're not able to solve those applications by those mathematical models. So the first question is how we're going to have a new model which is able to describe the partially observable information. So first thing is we talk about the new model, which is called partially observable Markov transition process. It's called POMDP. So to specify a POMDP, we only need to specify the following elements. So it's very similar to MDP. It's kind of like some set of states, set of action. So we have the following elements. We have S, A, and now we have a new set O. We use T and O and R and H. Okay. So we have a bunch of things like this. So we will specify one by one what are those things. The first thing courteous is again the set of states. We kind of like very familiar with this in MDP. The only difference is now this state is hidden. So to be clear, we say it's hidden states or latent states. So set of A is a set of actions. Again, it's a control problem, it's a decision-making problem, so agents always have a set of available actions and the agents can take at every time. So the new thing here is we have this O set. That is a set of observations. So basically, we know states are hidden. We're no longer able to observe the states. We only observe some partially things reflected some part of the states. So this is our observations. So those are three sets. So the remaining things, T, is actually just the transition probability. Okay, so this is something similar to MDP, or basically the same as MDP. So we have a probability transition that condition on the previous state and action. What is the probability transition to the next state? So for underlying states, it's still a Markov transition. Okay. So this is like transition to the next states. And for episodic setting, we also have a TH here. And the reason now we no longer use P, we use T, is because in PoNDP, we have another probability. So this T is one probability that uses transition. The O here is another probability that I call it emission probability. So this is the new thing, and sometimes it's just called emission. So emission is a probability that assume at each step, if we start from some state S, what is the probability I'm going to observe some observation? Okay, so this is, again, a stochastic process. So finally, we have R, that is a reward function. And the slight tricky thing is if we assume R is like is a function of underlying states and action, then it seems like the reward information might also leak some information about the states. So here, for the partially observable environment, for simplicity, we just assume all the information is already in this observation. Like in a sense, like you can think reward is also part of the observation. So we just now make R to be a function of O, so that to avoid some information leakage. Okay. So basically, we're saying reward is a part of the state, is a part of the observation. Finally, H is the horizon, the length of episode. Okay. To summarize the new model PoNDP, the only difference is now we have a new set that is observation, and observation will generated by some probability specified by the emission that is basically conditioned on the current states. What is the observation going to generate? And to avoid information leakage, we kind of specify reward as a part of the observation. So whenever I'm given the observation, I can immediately read what is the reward. So it might be better to understand this like abstract PoNDP definition in terms of the flow graph, like how each state and observation are generated. I kind of also omitted there might be also initial state distribution μ1. Okay. But since we kind of also emit this for MDP, so this is fine. So there are three things. The first is hidden states. We start with some state 1, sit at the first step. Okay, we have some initial distribution over states. So what we will do first is we take the emission probability. This S1 is going to generate an O1. This is observable. Okay. And then at the first step, the agent is able to take some action A1. So similar to MDP, basically the state 1 and action 1 jointly decide what is the distribution of the second state. Okay. So this part is the same as MDP. And a different part is now S2 is again hidden. S2 is no longer observed. So S2 will also emit an O2. And then we take an action A2. that goes to the third states. So you can think this hidden Markov model is, the POL-NDP model is actually a hybrid of two models in some sense. So one thing is if we kind of ignore the observation, like we only focus on the lower parts, and if we ignore the observation, like we say the state is observed, then this part is just become MDP. It's essentially an MDP. The only difference is now the states are hidden, so we don't observe the states. And on the other hand, we can also look at the upper part. If we ignore the action, or basically saying this entire sequence is not controllable. So the upper part, for those of you who have taken a statistical course or like a standard like machine learning course, you will probably notice this is actually a hidden Markov model. HMM. Okay. Even nowadays, this is like still some like research topic. A lot of statisticians like still like working on this HMM. Like the EML, like the maximum likelihood algorithm is no longer that trivial. Like you need to run some EML algorithm, and even like now, when people study some foundations of language model, people are kind of saying language model. Some people assume language model satisfy some like HMM. Okay. But basically, you can observe from this observation that POL-NDP is a model that is definitely more difficult than both HMM and MDP, okay? Because only part of them is like MDP, part of them is HMM. So this relation will be a lot clearer by looking at this table. So basically, we have a few traits. One is like fully observable. And the other is partially observable. The other trait is whether it's uncontrollable or like controllable. So this is an uncontrolled process, and this is a controlled process. So in the fully observable setting, we basically focus on the fully observable and something can be controlled, that is MDP. So we know if for MDP, we remove the action, this just become a very simple Markov chain. Okay, state is just follow the Markov chain. So this is a Markov chain. So in a partially observable scenario, if we kind of like adding a layer, one emission matrix, emission like probability to Markov chain, this becomes a hidden Markov model. And here for partially observable and control sequence, now this becomes POL-NDP. Okay, so those are the relations of those four models. Any questions about the basic models? If no questions, similar to like MDP or a Markov game, the next thing we will do is like define the policy and the value. So one of the most complicated part about the poor MDP is we kind of like we need to recall that the important thing is first states are hidden. So we no longer observe the states. So although underlying the state chain is Markov, the new thing we observe is that observations are no longer Markov. That you can easily see, like if we just condition on this observation O2, whatever happened like before that and whatever happened after it is actually like correlated. They are no longer independent, so they don't satisfy the Markov property. So that's basically one of the biggest reason in MDP. Poor MDP, a lot of things are very complicated, just because this based on the observation. Like if we just hide this O2, and whatever happened in the like past is no longer independent of the future. So essentially, for a lot of partially observed applications, we notice this biggest difference between this observation, like the Markov property, is in MDP. Basically, we can make decision based on current states. Well, in general, for poor MDP, you can prove, I won't show it in the class, but basically you can prove, in general, we need decision to be made based on the entire history. So the intuitive reason is just because the observation is no longer Markov. So looking at the current observation is no longer sufficient statistics for the past. So that means if you just making the decision based on the current observation, the observation of the current step, then you are losing some information about the history and you are making suboptimal decisions. So the best decisions always like depends on the entire history. So that essentially you can remember in the poker, whenever you make some decisions, you will always consider like in the entire playthrough, like whether my opponent like raise first or pass, like fold or something like that. So basically, you need to inspect the entire history, and also for StarCraft or some robotics is also like that. You need to remember the history and use the entire past information to infer what might be the current states. So in this case, the policy, we no longer have the luxury of only consider the policy that depends on the current observation. We need to consider the policy that depends on the entire history. So we will denote the history by this. Let's say tau h. Tau h is denoted as all the observable quantities up to step h. So basically that is O1, A1, O2, A2, till OH. Okay. So this is everything basically we observe up to step H, where at the point we need to make decision. So this tau H history is in the set of where we have this curly O times curly A to the power of H minus 1 and Cartesian product with O. And we denote this as TH. So we said now we need to consider the policy that depends on the entire history. So now the policy just becomes a map. It's again, pi is a set of pi h from 1 to capital H, where h pi h is a map from this th. Okay. So it's the set of all possible histories to a distribution over X. This is like a randomized policy, but for poor NDP, because a single agent problem, it's still sufficient to consider a deterministic policy. So most important thing is now we need to make a decision based on the entire history. So because we said observation is no longer sufficient statistics, and the policy will depend on the entire history. So similarly, if we want to develop a similar theory like for poor NDP, we should also look at the value function. And now value function is also no longer just depend on the current observation because it's not sufficient statistics. The value function in general need to depend on the entire history. So basically we have the value function. So in general, it's quite difficult to define like a value function for the intermediate step. So it's usually we just care about the value function at the very first step. We can also define in the intermediate step that depends on the tau h, depends on the history tau. This would be defined as an expectation. If we taking action, future action following the policy pi, pi will depend on the history of summation of h prime equal to h plus 1 to capital H, RH prime, OH prime, condition on the past history is tau h. So the definition is very similar. It's just the summation of all the future reward. The only difference is now we need to condition on the history so that to make it well defined, because the policy in general depends on the history. So similarly, we can also define the Q value, QH pi, tau h. That's equal to expectation if all the action is taken according policy pi, and a summation of the future reward condition on the past history is tau h, and in the current step, I'm taking action AH. Yes.
I'm sort of confused on why these things depend on the history. Like, if you knew, like, I guess if you knew the, like, do you know the hidden Markov model when making this, or like, if you knew the state O, then could you just like Bayes rules back to the state S and then like?
If you know the state S, it's Markov, but if you know the state O, it's not Markov.
Okay.
So basically, state S, S2 is like, for example, here, S2 is a sufficient statistics. Basically, it summarizes whatever happens in the, summarize everything matters happens in the past that will be affected in the future. But the problem is O2, for example, is only part of S2. So S2 will generate O2. So O2 only consider partially information about S2. While O1 and the previous actions might also contain other parts of the S2. So basically, in order to get to the sufficient statistics, you need to look at entire history. Bayes rule back would not work. Like Bayes rule, you only have a guess on S2. It's not like you don't know S2. If it's deterministic, if this S2 to O2 is like a one-on-one mapping, then this is good. But in general, for example, I might have like S2 is like something like have four different states. And the 1, 2 state 1, 2 will go to first observation. State 3, 4 will go to second observation. Then if you just observe the first observation, you have no idea whether I'm on state 1 or state 2. Then you might need some other information to decide what is this. I think this is like intuitive argument, but like just to mathematically, you can just prove conditional, there's no conditional independence, so it's not Markov. Okay, so following the same methodology, principle of like reinforcement learning, the next step we'll do the Bellman equation. The vanilla Bellman equation is not about optimality. It's just about the policy pi, and this is we will derive this by just looking at the definition of value function. You can do some transformation and like essentially figure out the relation between VH and VH plus 1, QH and QH plus 1. So we'll, for simplicity, I will just directly write the answer, but you can check offline. So there are two equations. One is VH to QH, and the other one is QH to VH. So VH will be, again, like summation over AH, power of A, in the set of A. And this pi h, AH, given the history tau h, QH pi, tau h, AH. And the other thing is this QH pi, tau h, AH, is equal to the expectation of we have OH plus 1 sample from the emission, the probability of tau h, AH. So I'm just writing, it's a probability, but you can basically infer what is this probability by doing the Bayes rule and by plugging the TNO. And then RH plus 1, OH plus 1, and then plus VH plus 1, pi, tau h, AH, OH plus 1. Okay. So this is the next step value. Next step value will depend on the entire history. That is the previous history append with the current action and the next observation. So other than you need to compute what is the probability you're going to sample the next observation according to this transition and transition emission and the Bayes rule, and everything else is like basically the same, other than like you just replace the states by the history, tau h. And similarly, we can also write out the optimal policy and the Bellman optimality equation. So very similar to the MDP setting, basically the optimality equation is just replace this the equation to get V from Q, like replace this integration over the policy by maximization over the action. So just something like this, VH star, tau h. That given the history tau h, the value of optimal policy is equal to max A QH star tau h. And the second equation is basically just a copy of what we have on the standard Bellman equation. OH plus 1 sampled from probability that will give tau h, AH, RH plus 1, O, H plus 1, and plus VH plus 1 star, tau h, AH, OH plus 1. And finally, optimal policy is just taking greedy policy over, it's just greedy policy of the Q star. So at a tau h, the best action you take is just the arg max. Of QH star, tau h, AH. So basically, following the same way we study MDP, this would be the first line of things we can possibly get, that we define the value, and we look at the Bellman equation, and we kind of like do the Bellman optimality equation. That is basically give us the optimal value. So what is not very good here? So typically, when we have the Bellman equation or Bellman optimality equation, we can like compute the, in the MDP case, we can compute the Q star and V star by the by like dynamic programming, which is one very important thing, because dynamic programming and the computation, we kind of say the computation and the sample computation is basically limited by the number of states and action. But here we kind of can replace the states by the history, and we can basically very easily calculate what is the possibility of history. So in general, some history tau h has O, A. O is the number of observation, A is number of action, to roughly power of h possibilities. So this is very different from in the MDP case, where if we look at the V value only depends on the states, and equivalent only depends on state action, where state action only has SA possibilities, while here we have OA to the power of H possibilities. So this basically says even in a tabular setting, which you can think is a very basic point MDP setting, we just assume number of observation, number of states, number of action are all finite. In this case, just representing V or Q star table require exponential space. So this is more the same even in a tabular setting. Although we kind of write out the Bellman equation or Bellman optimal equation, we can like theoretically compute those values based on this equation, but it won't be efficient. Like the entire history has too many possibilities, and we also require exponential space to store it. And this entire thing basically cannot be computed in a computer. This is also why PoNDP is somehow challenging. So we'll first talk about some alternative view for PoNDP, which you might think they can solve the problem, but we will say later it actually cannot. And later we talk about how we're going to partially solve some of the problem. So basically, this view of PoNDP is we kind of expand everything that depends on the entire history. There are historically also another very popular view that basically called belief states. So the idea is called belief states. So what is that? Let's first recall that in a PoNDP problem, we have this S1, O1, and that will generate S2 together with A2, A1, and then that generate O2. So at this point, we need to make decision A2. And that will transition to S3, something. So basically, we can look at this step where we need to make this decision. Okay, at this time step where we need to make decision A2. So we're saying the entire complexity about why we need to look at the entire history is because if we just look at O2, that's not sufficient statistics about the past, what happening. Basically, it only contains partial information of S2. So this O2 is not enough to make a better decision. We need to basically look at O2, O1, and A1. But to be honest, this S2 is the sufficient statistic. It's the only thing is we don't know. So a better idea about the belief states is kind of saying, how about let's just compute the distribution over S2. So basically, we can use history to compute a distribution over S2. And the observation is that S2 is sufficient statistics. Now we don't observe S2, but we can compute the distribution of S2, and this is basically everything we can conclude from history. And turns out this distribution will be a sufficient statistics about the past. Basically, once you know the distribution over S2, although you're not fully certain about S2, but once you know the distribution over S2, whatever happens in the past is no longer relevant to predict the future. So this is called the belief states. So basically, I no longer know whether my second step, whether it's in state 1 or state 2 or 3, but I can basically have a distribution that with 1/2 probability is in state 1, 1/2 probability in state 2, or 1/3, 1/3, 1/3, something like that. And this distribution is called the belief states. And this is a sufficient statistics. Of the history to predict the future. So basically, by sufficient statistics, we're talking about, for example, there might be 2 different histories. And as long as the two different histories give the same distribution over S2, the distribution of what happens in the future will be the same. So that means like once the sufficient statistic that distribution over S2 is the same, like although history might be slightly different, but it doesn't matter. Like in terms of the future distribution will always be the same. Okay. So formally, we say this belief states. We will denote this belief states as a BH. That's in a simplex of S. Okay, so it's a distribution over states. So informally, we will basically show that PONDP has an alternative view. The alternative view for PONDP is basically saying we can this view PONDP as a MDP in belief states. So now once we're in this view of belief states, so basically we can define a policy that now operates on the belief states. That pi h will now become a map from belief states space that is simplex over S to simplex over A. It's a lot cleaner because we no longer look at the entire history, but we just look at some probability distribution over the states. This only needs to rely on sufficient statistics. So the first thing is about, like we're just talking about very abstract about what is belief states. First, how to compute belief states. So we need to update the belief states based on the new observation and the new action. So basically, belief states is a vector, bh plus 1. We can look at each coordinate of the vector. That is, what is the probability of the process will be at the state sh plus 1 is equal to, we can do the Bayesian rule. That is a probability of sh plus 1. We are at this state, sh plus 1, and also observe observation oh plus 1 given the prior belief states bh and taking action ah, divided by p probability of only observation oh plus 1 and conditional bh ah. And this probability can be computed by TNO. By plugging the transition probability and the emission probability. So what does this gives? This is basically just by Bayesian rule and how to compute the probability of the next belief states in the next step based on the belief states in the prior steps and the new observation, new action we take, and new observation we see. So in general, this is like of the form that BH plus 1 is equal to some function f, where f is defined in this way, of previous belief states, and the new action I take, and the new observation I see. So you can use this recursive equation to just compute the belief states step by step. So in the very beginning, we don't have any, like we have probably the belief states in the 0 step is just initial distribution. And then we look at and this is like basically initial states, initial observation, initial belief states. And then at the first step, I take action A1, the second step, observer O2, and then I can update the belief states for S2. And then you can go on and on. So once we have this, once we know how to compute the belief states, we can now write down the value function and again, Bellman equation for that. So value function. Good thing now is this VH pi. We no longer need to write it in terms of the entire history. BH, that is equal to E pi H plus 1 H prime summation of all the future reward RH prime OH prime, and now condition on the belief states BH. So you can think this BH is that serve as a SH. The only difference now is not at a single state, it's at like a distribution over states. And we also have a QH pi, that BH, AH. This is expectation of a summation H prime from H plus 1 to capital H. RH prime OH prime is basically the same thing, summation of all the future rewards. Given current belief states is BH, and at the current step, I'm taking action AH. Bellman equation is also essentially the same. That's VH pi BH is equal to summation A in A pi H. AH given VH, QH pi BH AH. And similarly, we have QH pi BH AH. That's equal to the same thing. We're taking expectation over the next step observation that are going to generate it from Now condition on the belief state at H step and action at H step. RH plus 1, OH plus 1, plus. So the only difference is now this value will only take in the belief states. And so different from the previous Bellman equation, the value taking the entire history. And for the history, we just append the new AOH plus 1 and AH to it. And now the value only taking the next states. But the good thing is, fortunately, we have this update. So we can compute the belief states for the next step. So the input for the value at the next step is basically just the update of current belief states, and we take action AH, and we observe the new observation OH plus 1. Okay. So I just directly write the answer because everything is not very hard. It's just directly by the definition. And very similarly, we also have a Bellman optimatic equation. I will just omit the details. You can imagine this Bellman optimatic equation is basically just replace this with max, with maximization over A. And this will give our V star, Q star, and also pi star. So mathematically, this looks a lot cleaner because now we no longer depend on the entire history. We only depend on the current belief states, and presumably belief states is just the augmenting original state, which is a table now become a function over a distribution. And this might make it a lot easier to learn. And this is also the belief for a lot of people. But in general, whether this is true. Whether in general, by looking at point dp as in the viewpoint of belief states, whether it will reduce a lot of computation or efficiency, space complexity. So our intuition is probably no, because we're not doing anything very special or very significant. We're just basically reformulating the problem in terms of using the Bayesian rule and using the belief states. So we're not significantly simplify the problem, or we're saying we use some specific property where in the previous formulation we haven't used. No, here we don't have new property we discovered or anything. So intuitively, this should not be helpful in terms of reducing the computation. So what would be the missing part here? Why this is not helpful? So our intuition of this helpful will depend on one condition, that V star is a simple function, for example, is a linear function. So this basically says this would reduce computation. If V star or Q star is a simple function on B. Because belief states now is a continuous space, so it can be everything in a simplex. So if the Q star or V star is a simple function, for example, is a linear function or quadratic function, so we only have limited number of parameters, then this, of course, will reduce a lot of computation because previously everything is exponential. Now we only need to fit what is V star, what is Q star. But the problem is this is actually a strong requirement. For now, I think in the literature it's quite unclear what kind of point dp would generate a simple function. So we're lack of understanding of what kind of a sufficient conditional problem structure that will generate this simple function on Q star or V star. And in general, if we don't assume any assumption, So in general, if we don't like making any assumption on the point NDP, it just can be generic point, tabular point NDP. V star B is actually not linear in B. So it's not a linear function in the like belief states. So basically, it's slightly counterintuitive, but if you think it more, it actually makes a lot of sense. So for V star, for example, if you know the value, like for the value, if you know the state is in the state 1, or if you know the state in state 2, and this average of those two values will not be equal to, like for example, if you know that currently the belief states is 1/2 in both states, because the middle, like the last scenario that if you're uncertain about the states is actually much harder. So in general, this is definitely not a linear function. So you can actually even prove that in general, if you don't have any structure, that will be, actually it is to be piecewise linear function. So if the function is piecewise linear, one of the complexity that measure this function, how complex this function is the number of different pieces of this function has. And unfortunately, you can actually prove the number of pieces in general. Can be exponential in h. So basically, this is still computationally intractable. Okay. So basically, as we said, there's no free lunch because although we can write everything in the belief states, but belief states is a kind of continuous variable, so it has a lot of possibilities. And the value is actually not a simple function of B. It's like a piecewise linear function where you have exponential number of pieces. So just to specify the V star, specify this piecewise linear function has exponential pieces, that already requires some exponential space, which basically make everything like intractable. Okay. So basically, when we do this Bellman-Optionality equation, we're implicitly talking about the planning. So we so far have been talking about two planning algorithms, which is using Bellman-Optionality equation on the entire history, or using Bellman-Optionality equation like on the belief states. But both of them are computationally intractable in general. So you may wonder whether there's a better algorithm. So it turns out it's not a fault of like belief states or like a history. It is just the entire problem is difficult. So there are some computationally hardness result. So this is for planning. Basically, even if we already know what is transition and what is emission, we already know a TNO, and when we want to compute the optimal policy. So in general, you can say if we want to compute the optimal policy, the truly optimal policy that is history dependent. So this actually is super complicated. So you can actually prove no algorithm is able to like find this optimal policy in polynomial time. And in fact, this is like p-space complete. For those of you who have no idea what is p-space complete, I hope you have heard of what is NP-hard. So basically, p-space complete is something, even harder than NP hard. So it's like more complicated. So definitely we have no idea what is the polynomial algorithm for it. And people also kind of have investigated some subclass. For example, this is about a truly optimal policy. So what if I don't care about the truly optimal policy because it kind of depends on the entire history? What if I only care about the subclass of policy that's like so-called memoryless? Okay. We kind of like say for point NDP, we can no longer just if we want to make the optimal decision, we can no longer just look at the current observation. But this is saying, okay, like this general policy is like too hard. I only want to look at the memoryless policy. That is, I basically make decision only depends on the current observation. So I know this policy may not be very good. This policy may not achieve the global optimal. But this is like my easier version of objective. I just want to basically compete with all the memoryless policy. I just want to do the best within this subclass. So it turns out even if you just want to find an optimal memoryless policy, the complexity is actually also NP hard. So it's slightly better than P-space complete, but not much better. Basically, it's not even in P. And to make it worse, there are also some statistical hardness result. That is, even if we allow infinite computation, so basically, this part is saying even if I ignore the P-space complete NP hard, I have like some supercomputer which is able to compute everything extremely fast. Then like the learning problem is still difficult. So these are completely two perspectives. This is basically saying like learning is solved. Like I already know the transition and emission, and then computation is hard. And this is saying if I have infinite computation, but I don't know the model, I don't know TNO. And statistically, it's hard. It's basically it says require learning point NDP. Omega A to the H samples in the worst case, even if I have infinite computation. So far, it seems we have introduced a very elegant model for partially observable, and we are kind of convinced it's a very important problem. And we have derived some like basic foundations. But in terms of reality, like if we want to do computation and if we want to do statistics, everything seems like very difficult. And this has been like this in the field like for decades. And even till today, I would say computational efficiency is not well solved. So basically, this is already a hardness result. So the way to circumvent this is basically by looking at some subclass of problem. We're seeing in practice, the problem is now like worst case point NDP is only a subclass of problem which we're interested in practice. And even for that, computationally, we can basically improve for some subclass of point NDP. We can improve this kind of very bad complexity to something quasi-polynomial. Still polynomial, but still not polynomial, but polynomial to some like log factor. Well, in the next lecture, we'll introduce some very recent results about how to circumvent the statistical hardness by looking at some like a subclass of problem. So basically, we will look at why there is some statistical hardness. We look at what is the hard instance, like what is the point NDP that prevent us from efficient learning. And then basically, we will notice those point NDP are not very interesting point NDP. They are like a trivial point NDP, which we know is definitely hard. So the way we solve this problem is we can rule out this certain part of point NDP to make it like more efficient solvable. And we will develop an algorithm to address the statistical problem in the next lecture. Okay. And just to be clear, next Tuesday we won't have lecture, and we will have very last lecture on next Thursday. Okay, that's in the email.